We're here at Google this afternoon with Matthew Inwood, and we're going to be talking about how computers actually work. Matthew, it's great to be here this afternoon. Thank you very much for having us. So, how do computers work?
So, I think the basic model is data goes in. There's some sort of transformation or something happens with that data, and then data goes out afterwards. Where data is really just numbers, I suppose. And all computers work in exactly the same way, where the input and the output may not always be obvious, but for example, in a mobile phone, the input and the output will be the mobile network, and it may be talking to the internet. So there's input and there's output going on the network. The phone is processing that in some way, and the CPU itself is just taking this input, it's processing it according to the instructions, and then providing output from that. Yeah.
So, I have this mental model of the CPU takes the program which is stored in memory and executes the instructions that make up that program. But what actually happens in the CPU itself when that machine code gets executed?
There's a program called a compiler, and so when you write your program in sort of human readable text, and the compiler's job is to take that human readable text that you've written and convert it into machine code that can be executed directly onto the CPU. And it's a fairly complex process, but it involves what's known as parsing the text, which is like understanding the structure of it, performing numerous analyses on it in order to understand exactly how it works, and then the end result of that is just binary machine code that to at least most people would be completely unintelligible, but that's what the CPU sort of understands.
But some languages are interpreted rather than compiled.
So some languages are interpreted, and there's a lot of similarity between an interpreter and a compiler in terms of like the understanding of the structure of your program, sort of understanding the text that you've written is sort of common. But an interpreter, and what it does instead of writing all of the machine instructions out ahead of time, it does it sort of as you're going along. So it will interpret a part of the program, and then it will convert that into machine code, or maybe it will just interpret it in place, and it will be a program that directly executes sort of the text input on the CPU.
Okay, now walk me through that next step. Once you have this as machine code being executed by the CPU, what does that actually mean? What's happening inside the CPU?
Okay, so the CPU is a huge, complex bit of silicon, or huge, sort of logically, if not physically. It's hardwired to understand the machine code that you give it, and it takes each instruction in the machine code it will take, and it will convert that into a big list of individual actions to be taken to execute that instruction.
Is this what we call microcode?
Yeah, so this is microcode, exactly. And so microcode is like a big long string of bits, each bit being an on-off switch. And each of those on-off switches is effectively turning on or off a specific bit of circuitry inside the CPU. For example, if you have an add instruction, then it might say turn on the add circuitry. And so that will then take the two bits of data, it will add them together, and then there'll probably be another switch somewhere that says, and the output from that, you want to write it to main memory, or you want to write it to some other part of the CPU. And the sort of all of the on-off switches and the bits of circuits, the individual circuits that activate, is sort of arranged. They can be arranged so that one bit takes output from another bit. So you might, for argument's sake, you might have you have the add bit, and then you might have something else that tells it to do a bitwise shift operator, so shift left or shift right, and you can sort of make these sort of slightly more complex machine instructions that will do these multiple things, and then again, as I said, you can write it to a register, and you can write it to main memory or something like that.
I suppose there are layers of abstraction.
Yes.
That your typical 14-year-old at school doesn't need to worry about.
There are many layers of abstraction, and when you study how CPUs are built, it's sort of mind-boggling how much abstraction there is, and the fact that it is all built in silicon logic, in transistors and so on is it's amazing. So there are layers of logic. So you will have like arithmetic, and you'll have information about where to get the input from, where to run the output to, and like so many other things in there as well. And a lot of huge amounts of complexity to do with making it go faster and things like that.
Yes. So, what sort of mental model ought one to have? Is there a particular way of thinking about this, which helps understand what's going on here?
Yeah. So it's to understand sort of the idea of layers of abstraction. You can think about a restaurant. So in a restaurant, you can go and you can order off the menu. And to order off the menu, you don't really need any information about how the dish is prepared, what ingredients it uses, all of these sorts of things.
We trust other people to do
we trust exactly. Yeah, and so I guess you can consider that as like being analogous to like writing in a high-level language, and then your order will go to the kitchen, and in the kitchen, maybe the chef tells the cooks like we need to chop these things, we need to how to cook them. But again, that's sort of fairly high level. The chef isn't telling you, isn't telling the cook. They're not telling them how to use a knife and how to slice a carrot or whatever. They're just giving them
trusting them to do that.
Exactly, trusting them to do that. And then obviously the cooks, it's like they're sort of working at a lower level again. And so maybe that's closer to sort of the machine code level. But then even then, the cook doesn't have to know how the ingredients were produced. How the cow was bred, how the carrot was grown, these sorts of things. So that's again a different level of abstraction.
Physical electronics.
Yeah,
it's another matter entirely. Yes.
So yeah, I mean it's not a perfect analogy, but it does give you an idea of like layers of abstraction and how at the level of the menu you're at quite a high level of abstraction, and maybe you could even go a level above and say, well, you have an Italian restaurant, you have a Chinese
where shall we have lunch?
Exactly. Yeah. So you can sort of take it up more and more layers of abstraction, and I guess at each level you have less control over how the actual what you're eating is produced, but you have sort of more power to it's a lot easier to go into a restaurant and say, I'd like some spaghetti bolognese, than to go and grow a cow and make some spaghetti and all the rest of it.
So Matthew, tell me, how has your understanding of how computers work changed over the period that you've been working or studying this area?
Yeah, I think the biggest shift in how I understand how computers work is really to do with how computers have changed.
Okay.
So when I first started programming, a computer was a big beige box that sat on the desk with like a clunky TV set on top of it, and they were pretty simple. They didn't have very much storage. You maybe didn't have a network connection at all, and there would have been a single CPU in there, whereas now you may have several. And critically, they'd have been plugged into the mains all the time, so there was no worrying about how much battery, how much power it used, because it didn't matter. And now you're operating with mobile phones. They're obviously they're completely different in every regard. I mean, they're fundamentally the same. The input, processing, output we discussed earlier, it's the same thing. Yeah. It's just smaller and it's faster and it's more battery efficient or more power efficient, I should say. But yeah, the fact that now it goes in your pocket, it's not plugged in all the time, then the amount of power used, much electricity used by the CPU becomes really important, because you can't just you can't just use as much as you like, because the phone will last for 2 hours and then you have to recharge it. So yeah, that's a pretty fundamental difference to how we work now.
Whilst the fundamental principles have stayed the same over this time.
Yeah. And there are things get more sophisticated with time, but the fundamentals are exactly the same.
But the things that you need to take into account when programming or designing software for these systems do change over time as the technology has evolved. Okay, what do you think a 14-year-old ought to know about this level of detail?
I think in order to understand, or you'd want to understand the sort of the basic input-output we discussed.
Yeah.
That's essential, and I think understanding how that relates to the sort of computers that a 40-year-old is familiar with is quite important, I think, because it makes it more understandable, I guess. So, as I said, input and output doesn't, with a smartphone, you don't really think of it having input and output, but it does. Input is you touching the screen, and the output is the what's visually on the screen, and it will also be talking to the mobile phone network. That's input and output. So I think it's good to understand how those things work. I guess a basic understanding of how the CPU works, so like the fact that it does very simple operations like adding numbers, subtracting numbers from each other, just storing data or shifting little bits of data around in sort of very, very simple operations. And it's sort of, it's a big jump from there to understanding how Angry Birds on your phone works. But just sort of trying to have an appreciation that these things, these big complex things, are built out of these tiny little individual simple operations.
This model of multi-layered abstraction that's inherent in computation.
Yeah, and obviously you can't make a mobile phone just using simple bitwise or arithmetic operators, but by building many layers of abstraction on top of that, then you can.
This is how the problems get solved. This is what computing and computer do. Use the bits that other people have made.
Yes, exactly. Yeah. And so as a software engineer, you will never write machine code directly because you have a compiler. But then you'll probably never write the low level, the basic things the compiler provides directly, because there'll be more sort of layers of abstraction on top of that as well.
Whilst you're never writing at that level of granularity, I suppose, does an understanding of how the code gets compiled matter in software engineering?
It can do, but not always.
Not always, because we trust the compilers to do their job well. Yes.
It can matter, for example, if how fast your code runs is really, really important, and that's very rarely the case these days. But if it is, then you need to know the sort of technical details of how the CPU runs and how it operates. That can help to make things run faster, and also, of course, to make them more battery efficient, which is sort of the other side of the same coin.
So, as you say, the fundamental principles here haven't changed over a long period of time, but the technologies have. Does parallel processing make a difference? Does the way you think about algorithms or the way you think about programs change when you're dealing with lots of processes?
So when you have a single CPU and a single thread, you're doing one thing at a time, and it's all quite straightforward, really. It's just it's just a series of instructions that are run in order. By contrast, if you have multiple threads or multiple CPUs running in parallel, it gets a lot harder, because now you need to understand how these multiple things interact with each other, and so especially if you have got multiple threads or CPUs working, doing a single operation together, they need to sort of pause and synchronize sometimes.
Yes.
And so obviously this gets an awful lot more complicated. Especially, for example, on the internet, you might not have just multiple threads and CPUs. You might have multiple physical different machines.
Of course, yes.
And it's similar problems, but obviously the sort of delay between things, they're further apart. Messages take longer to get between them. And, so then you have lots of sort of synchronization problems, making sure that the operation of one part of the system doesn't interfere with another operation of another part of the system, and all these sorts of things. It's.
And what about quantum computing? Will that change the way we think about it?
So my understanding of quantum computing isn't great, but I understand sort of the basics, which is in a digital computer, you have a bit, and it's an on-off switch. Yeah. It's either one or the other. And that's pretty straightforward and easy to understand. With a quantum computer, you have it's a qubit, I think it's called, and it has so the quantum is all about the state of it is not known until you observe it, and when you observe the state, then it becomes fixed, neither one or the other.
Yes.
And so a quantum computer, while it's operating, it will have, instead of every bit, it's got a qubit with a potentially unknown unknown state, and then only sort of at the end, when you observe it, does everything sort of go and flip into one state or the other. So my as I said, my study of them isn't great. They are they seem to me a lot more complex than the regular computer.
Yes,
but also
sure.
also allow you to do certain things a lot faster than you could.
And will that make a difference to the way that computer scientists, software engineers think about the code that they write, or is this all at a level way below that?
No, I'm sure it will make a difference.
Yeah.
I think the code that you would write for a digital computer, running the same code on the quantum computer, I don't think would be taking advantage of sort of the quantumness.
Right. Yes.
So yeah, but I don't know. Quantum computers are still very, very early days and sort of researching. So
okay.
Yeah.
But potentially very interesting.
Yeah.
Sure. Okay. So summing up then, if teachers wanted to get into this low level of understanding computation, or they had students who were interested in working at this lower level of computing, what would be your advice to them? How should they get involved at this level of detail?
I guess it might be an interesting thing to do. So I said earlier that you would never write machine code directly because there's no reason to. But actually, if you did that as an exercise, it would give you a much better understanding of how the CPU is working at that very low level. And you can use what's called an assembler, which is something which takes instead of taking this sort of high level structured text that you write, it takes a very simple sort of form that you can write in text, but then it's compiled very literally into machine code. So each sort of word you write in the assembler is translated into a single instruction in machine code.
Sort of a human readable version.
Like a human readable version of it, exactly. So yeah, I think writing in assembler would be a nice way of just getting a better understanding of how the CPU works, and also getting an appreciation of all the work that the compiler or the interpreter is doing for you. Yeah. Because the sort of what you can do with assembly or machine code is a lot lower level, a lot more basic than what you can do with a compiler. In terms of how the CPU works internally, I'm not sure there's much you could do other than read about it on the internet or something like that.
It's a good place to start, I'm sure.
Yeah.
Matthew, thank you ever so much for your time this afternoon. Really interesting. Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.